Hello and welcome to GER Hub Mathematics and Statistics lessons. In today's video, I'm going to be talking about the inverse element of a binary operation, the inverse element or the inverse property of binary operation. So if you haven't subscribed to the channel, please smash a like on this video, turn on your notification bell and click the subscription button. I will be seeing you in this video. Welcome to my class on binary operations. In particular, I'm going to be talking about the inverse element, the property of the inverse element. So come with me, let's begin this class. So let S be a non-empty set that is closed with respect to a binary operation, say asterisk. Then for any element A that is a member of S, if there exists another element, A prime that is also a member of S, such that this condition I'm going to write holds, that is A prime asterisk A is equal to A asterisk A prime and is equal to E. Then A prime that is a member of S is said to be the inverse element. So what am I saying? Now, the property I've written on the board is the property of the inverse element. What it means is this: unlike the identity element, every element in a set, a non-empty set that is closed with respect to a binary operation, can actually have an inverse element. All it takes for that element to be called the inverse element of another element is that the inverse element has the power of combining with any specific element to give you the identity element as its result. So if you pick an element from a non-empty set and combine it with what is presumed to be the inverse element of that particular element, it will combine to give the identity element. Now, let me give you a quick example of the inverse elements we've been using over time with respect to multiplication. If you've ever done this, what is the inverse of 2 with respect to multiplication? The inverse of 2 with respect to multiplication is 1 over 2. Why is that so? With respect to multiplication, the identity element is 1. And the only element that can multiply 2 as a number chosen from a non-empty set, say the natural number system, to give you the identity element 1 is 1 over 2. So because 1 over 2 has the power to multiply 2 to give you the identity element with respect to multiplication, then 1 over 2 is certainly the inverse of 2. Now, I must explain at this point the difference between the inverse element and the identity element. The identity element remains unique and 1 for the entire elements in a particular non-empty set. So you cannot have identity elements changing with respect to elements. But for the inverse element, as you move from one element to another in the non-empty set, there is every tendency that you will end up having a different inverse element. So the inverse element with respect to multiplication is 1 over 2 for 2. Does not mean that the inverse element with respect to multiplication for 4 will be 1 over 2. So why is that so? 4 times 1 over 2 will not give you 1. Okay? But 4 times 1 over 4 will give you 1. And that means that the inverse element with respect to multiplication for 4 is 1. Okay? Is 1 over 4. The inverse element of 4 with respect to multiplication is 1 over 4 because 1 over 4 multiplies 4 to give you 1. Okay? Now, if you move over to addition, what will be the inverse of 2 with respect to addition on the natural number system? It will be minus 2. And why is that so? Remember our discussion on the identity element with respect to addition for the natural number system was 0. Okay? So what number would you add to 2 to give you 0, the identity element with respect to addition? it is minus 2. So since minus 2 can add to 2 to give you 0, which is the identity element with respect to addition, then it means that minus 2 is the inverse of 2 with respect to addition. And again, because minus 2 is the inverse of 2 with respect to addition does not mean minus 2 will be the same inverse for every other element in that non-empty set. No. As you move from element to element in a non-empty set, the inverse element changes. But as you move from element to element in a non-empty set, the identity element remains constant. And I want you to take note of this. So, 4 is an element chosen from a non-empty set, say the natural number system. What is the inverse of 4? The inverse of 4 is not minus 2. It must be 4, minus 4. And why is that so? It is because minus 4 is the only number that can add to 4 to give you 0, which is the identity element with respect to addition. So the question is this: have we been doing this over time in ignorance? Yes, we have. Over time we've been doing this. We've been using the inverse element in ignorance, and you must take note of this simple fact. This all along has been an application of this knowledge, the knowledge of the inverse element. So let us take an example to show you how to solve problems using your knowledge of the inverse element. So let S be a closed non-empty set on which a binary operation, say asterisk, is defined by A asterisk B is equal to the square root of AB all over 2. Okay? So if this is a binary operation defined by this, we want to obtain, the question requires that we obtain the inverse element. Now, this question demands that I explain to you something you must know. Now, you cannot solve any problem involving the inverse element without having a knowledge or without solving for the identity element. If given a problem on the inverse element, you must start with getting the identity element. So I cannot solve this problem on the inverse element without solving first for the identity element. So we are going to start the solution to this problem over here. Okay, quickly. So this is what I'm going to do. As a solution to the problem, let us start with obtaining the identity element. And I'm going to show you why that is needed. So recall that A asterisk E equals A implies that E is the identity element. Okay? So if E can combine with A to give back A, then E is the identity element. Now, we are told that A asterisk B is equal to square root of AB all over 2. What does that mean? It implies that A asterisk E will be equal to the square root of AE all over 2. Now, since we want the identity element, then A asterisk E, which is equal to square root of AE all over 2, must be equal to A. And why is that so? If E is the identity element, then it has the power of combining with A to return A. Now, A asterisk E, by definition of the binary operation given to us, is square root of AE all over 2. And square root of AE all over 2 would surely give us A, since E is presumed to be the identity element. So I'm going to simplify. AE would give us 2 times A when you make A square root of AE the subject of formula. If you square both sides, the square root of AE has to be the square of 2A. Now, squaring both sides implies that this returns AE and this will return 4A squared. What am I trying to do and why am I doing this? It is simply because I must obtain an expression for E. I want to make E the subject of formula. I must get the value of E. So let's come over here and get the exact value of E, the identity element. Now, if I make E the subject of formula, A will divide both sides, and that will give me 4A squared all over A, and this implies that the identity element required is 4A, since A will cancel one of these A above to give me 1A remaining. So the result becomes E equals 4A. Now, The problem did not require that I get the identity element. The problem requires that we obtain the inverse element. But you cannot obtain the inverse element without obtaining the identity element, and that is why we started with obtaining the identity element. Now, for the inverse element, let A prime be the inverse of A. So let's assume that A prime is the inverse of A. According to property, then A asterisk A prime must give us the identity element. So the condition of the inverse element requires that we combine what is presumed to be the inverse element with any element at all, because that will certainly give the identity element. You can now see why I needed to get the identity element, which gave us 4A. So what this means is, if A asterisk A prime gives E, then it means that A asterisk A prime will become the square root of A prime all over 2, giving me E. Okay? Now, how did I get this? This is coming directly from the question. Anything asterisk anything will give you the square root of the product of the two of them divided by 2. So, if I'm given A asterisk A prime, then A asterisk A prime will give me the square root of A times A prime all over 2. Now, if A asterisk A prime is equal to E, it implies that the square root of A asterisk, the square root of A prime all over 2 must be equal to E. What did we obtain as E? E was obtained as 4A. So I'm going to bring that here. Square root of A prime over 2 is equal to, instead of putting E, I'm going to put 4A. Okay? Now, I'm going to bring the problem over here to conclude quickly. So let's see what will be done here. Now, so bringing the problem over here, what am I interested in? I'm interested in getting A prime. So I'm going to make A prime the subject of formula by doing this. So square root of A prime will be equal to 4A times 2, which was the denominator on this other side, and that will give us 8A. Okay? Now, if I take the square of both sides, this will give me the square of the square root of A prime A, and this will give me the square of 8A. Okay? Squaring both sides implies that the left hand side becomes A prime, and the right hand side becomes 64A squared. Okay? Now, since I want A prime, I'm going to divide through by what stands beside A. A prime, that is the coefficient of A prime, and the coefficient of A prime is A. So this becomes 64A squared divided by A, and that will cancel to give us 64A. So what does that mean? It means that the inverse element is 64A. Now, if you want to check if the inverse element we've obtained is actually correct, then we would establish that using the property. Let's see if A prime A gives us E. Now, A prime A is the same as square root of A prime all over 2. And that will give you the square root of A times A prime, which we have obtained to be 64A all over 2. And that will reduce to 64A squared all over 2. And that will finally reduce. The square root of 64 is 8, and the square root of A squared is A all over 2. Take note, dividing these gives you 4A. And what is 4A? 4A is E, the identity element. And that shows you that the answer is correct. Okay? So if you want to solve problems on the inverse element, you should follow the procedure, state the property, and follow thereof. All we have followed in order to get to the solution below. Okay? Now, if you want more questions to be solved on binary operation as it concerns the inverse element, then send a comment to me in the comment section below, and I will reply accordingly. That being said, thank you very much for watching this video. If you haven't subscribed to the channel, please click the subscription button, smash a like on the video, turn on your notification bell, and I will be seeing you in my next class on any other topic I will be choosing subsequently to talk about. Thank you very much.